Today we need to talk about sampling or sampling, as Texans would have it. This has been at the core of much of what we've talked about already, and we've talked explicitly previously about the need for sampling in social research, in fact in all kinds of research. You and I understand, and I'm sure that you understood before you came in this course, you didn't need me to tell you, that researchers are interested in populations of people. And populations does not mean everybody out there, necessarily. In fact, it rarely means everybody out there. We could talk about populations of males or females, populations of males or females over a certain age, populations of males or females that engage in some behavior. They eat red meat, they consume caffeine, they smoke, whatever it may be. We could talk about a population of fifth graders. The point here is that, first of all, that researchers are interested in populations of people, but those populations need not, and rarely do, involve all individuals out there. The problem for researchers is that those populations are typically inaccessible. If you are interested in women recovering from mastectomies, how would you go about sampling randomly from, or sampling from that group? Or even, at this point of the discussion, I guess, how would you define that population specifically? I mean, you're depending upon other people. You're depending upon surgeons or physicians to provide you lists of those women who've had a mastectomy within some time period. And you and I know that those lists are often inaccurate. Names get on the list mistakenly, names are omitted from the list mistakenly, and so on. So it's very difficult, even at a very basic level, to define the population that you're interested in. And to then access that population, interview or question or observe every member of the population is so obviously impractical for the most part that I think it doesn't require any further discussion. What researchers then do is select subsets of populations. That is, a sample from those populations. And how they go about doing that affects the validity of the research. It affects the reliability of the research because it affects the reliability and validity of the data that are generated. But the basic issue is that researchers intend to make statements about populations, but are forced to rely upon samples, subsets of those populations. The topic then for today really is how researchers go about selecting those samples. And the preferred method, the most preferred method of sampling is random sampling. The most preferred method of sampling is random sampling. And in this context, random does not mean what you and I take it to mean often in conversation. That is, it doesn't mean haphazard, it doesn't mean accidental, it doesn't have any of those sorts of conversational meanings. It has a very specific meaning. Random sampling occurs when all subsets of size n, random sampling occurs when all subsets of size n, uppercase N, as in Norman, when all subsets of size n have an equal probability of selection. Have an equal probability of selection. And the key here is equal probability of selection. this definition simply means that all subsets of the same size, whether that be an n of 6 as it is in the lottery, or whether it's an n of 142, that all subsets of that size have an equal probability of selection. In the lottery, that is the case because those numbers, the winning numbers, are selected randomly, so that the likelihood that 1, 2, 3, 4, 5, 6 will be selected is equal to the likelihood that 9, 21, 32, 38, 41, 48, and 50 will be selected, which is equal to the likelihood that any other configuration of 6 numbers will be selected. Ultimately, this reduces to the statement that, or the requirement that, all individuals have an equal probability of selection. If that is not the case, if there is not equal probability of selection for all subsets of size n, or for all individuals, then, however the sample is being selected, it is not being selected in a purely random way. So, first of all, researchers, the objective that researchers have is to make statements about populations. Secondly, those populations are almost uniformly inaccessible. So that, third, researchers have to rely upon samples, subsets of the population. And four, the preferred way of selecting those subsets, selecting those samples, is through random sampling. And to sample randomly requires that researchers ensure that all subsets of size n have the same probability of selection. Let's make a couple of observations about that. First of all, even if a researcher samples randomly, he or she is not guaranteed that the resulting sample will be representative of the population. For example, if we were to have a normal distribution, a population of intelligence scores that were distributed normally, we could reach in randomly and select out an entire sample comprised of low scores, low intelligence scores. We could reach in randomly and select out a sample comprised of high intelligence scores. Would you agree that if we did that, these samples would not be representative of the population? They would not be a mirror image of the population. That is, even if you sample in the preferred way, even if you sample randomly, you do not guarantee that the samples that you select will be representative of the populations from which they are drawn. What you do guarantee is that you can treat those samples as if they were representative of the populations from which they are drawn. What you guarantee is that you can treat those samples as if they were representative of the populations from which they are drawn. And you can do that because when you sample randomly, the statistics associated with those samples, for example, X bar, are unbiased estimates of the population parameters, in this case, mu. When you sample randomly, the statistics associated with the sample, for example, the sample mean, are unbiased estimates of the population parameters, here the population mean. So observation about random sampling is, on the one hand, that it does not ensure that the sample will be representative of the population. But on the other, what it allows a researcher to do is to treat that sample or those samples as if they were representative. Because the estimates that they generate are unbiased estimates of the population scores. A second observation to make about random sampling is that it is typically impossible. Pure random sampling is typically impossible. I was talking earlier about a hypothetical situation in which a researcher was interested in women recovering from mastectomies and observed that in doing that, the researcher relies upon others to provide information, surgeons and physicians and so on, and that information is often inaccurate, that names are included mistakenly and some names are omitted mistakenly. And that being the case, the researcher, would you agree, cannot even identify the population accurately. And if you cannot identify the population accurately, you cannot ensure equal probability of selection. Obviously as well, even if the data were accurate, even if you did have an accurate enumeration of the population, accessing all of those individuals in any reasonable way would be impractical as well. The bottom line of this is that while random sampling is the most preferred way of sampling, it is rarely used by researchers. It is rarely used because it is typically impractical. What then do researchers do? Well, they have developed two types of sampling. The first is probability sampling. The first is probability sampling. And I'm going to give you two examples of probability sampling. But in overview, probability sampling techniques, although they violate the mandate of random sampling, that is, although they do not guarantee equal probability of selection, they violate that mandate minimally. So in a sense, probability sampling procedures are good. Let me give you two examples. The first example of probability sampling is stratified sampling. Stratified sampling. An example of stratified sampling. If a researcher were interested in voting behavior and was using a stratified sampling technique, the researcher would first of all identify critical variables or critical strata in the population, critical attributes. And there are a number of critical attributes in the context of voting. One, for example, is gender, because males are more likely on average to vote Republican and females more likely to vote Democrat. So gender is associated with voting behavior. So too are other variables: ethnicity, religious affiliation, age. So we could select any of those, but gender is the simplest to discuss. Having identified this critical variable, this critical attribute in the population, the researcher would then identify all values of that variable. And clearly there are two values, and only two values, of gender. One is femaleness and one is maleness. That is sometimes not so straightforward. If we were talking about religious affiliation, there are a variety of religious affiliations. Perhaps hundreds of religious affiliations. And in that context, a researcher would probably have to limit the number of religious affiliations in which he or she was interested. But back to the issue of gender. Having identified the critical attribute in the population, having defined its values, the researcher would then sample in such a way as to ensure that each of those values, each of those groups, each of those types of individuals was represented in the sample. That is, in this context, the researcher would sample in such a way as to guarantee that both males and females were included in the sample. The minimum requirement there is that there be at least one male and at least one female. And you would agree, I think, well, on the one hand, I hope you agree, that violates random sampling. Because the researcher who pursues this strategy has negated a sample comprised entirely of females and a sample comprised entirely of males. And having done that, the researcher has violated the mandate of random sampling. What is more, because a single individual is unlikely to necessarily be representative of a group as a whole, one female is unlikely, I think you would agree intuitively, is unlikely to be representative of all females. Researchers typically place some greater requirement. For example, at least 30 females and at least 30 males. And a researcher who does that has violated random sampling because he or she has negated the possibility of samples comprised of less than, or including less than 30 females, and all samples including less than 30 males. But if we focus on the forest and not the trees, that violation of random sampling is relatively minimal. So that researchers who pursue a strategy of stratified sampling are using a probability sampling technique, and those techniques violate the requirement of equal probability of selection, but they do so minimally. So that the estimates that those such samples generate are minimally biased. A second example of probability sampling is what is called multi-stage cluster sampling. Multi-stage cluster sampling. And in overview, a researcher who uses multi-stage cluster sampling simply pursues a strategy in which she or he samples at multiple levels, moving from the most general to the most specific. Let me give you an example. If you belong to or a member of the Texas State Education Board, and you had some sense, you would, and let's assume that you've just approved a new history text for all fifth graders in public school in the state of Texas. if you had any sense, you want to know how effective that new text was compared to previous texts or compared to previous versions of the same text. It makes no sense to believe that you could go into all 5th grade classes in the state of Texas. So what you might do is to employ a multi-stage cluster sampling procedure in which you move from the most general level to the most specific level. And you sample randomly at each level. For example, you might first of all articulate or identify all the counties in Texas and select randomly from amongst those counties. Perhaps you select 20 counties. You now identify all of the school districts in those 20 counties, and you select randomly some number of those school districts. Perhaps you select 50 school districts. You now have 50 school districts. You identify each of the schools, each of the elementary schools, in those 50 school districts. And you select randomly from amongst those elementary schools. Perhaps you select 100 of them. You now identify all of the 5th grade classes in those 100 elementary schools. And you select randomly from amongst those. Perhaps you select 50 of them. And now you go to those 50 5th grade classes in those schools, and you administer your test of history. This is an example of multi-stage cluster sampling. It involves numerous stages, and at each stage you sample randomly, and you move overall from the most general to the most specific. In our example, we move from all of the counties in Texas to a limited number of 5th grade classes in public schools. This is in opposition to what actually happens, and that is we simply administer a standardized test. The motto in Texas is that if you weigh it, the more often you weigh the pig, the heavier the pig will get. The more often you test the child, the more intelligent the child will get. Just a little vent. Are there any questions?
Are you sampling everybody in the county, and then you sample everybody in the school district, or are you just selecting the counties and selecting?
You're just selecting the counties. You're not identifying individual 5th grade students in those counties. What you're doing is simply identifying the counties and selecting amongst those. And because you do that, although it looks like random sampling at each level, and it is random sampling at each level, and so you would perhaps conclude at the end that you've sampled randomly, that you haven't violated the mandate of equal probability of selection at all. If you focus here not on the forest, or not on trees, but on the forest, when you get to that last level, you've got some number of 5th grade classes you're sampling from. Well, at the very first level, you cut away a large number of possible 5th grade classes. This is the analog in the state lottery would be to at the outset to define odd numbers and even numbers and select only one or the other. And then having selected, and select that randomly, and having selected either odd numbers or even numbers, perhaps to then define levels of those numbers, less than than 10, between 10 and 19, and so on up the scale, and then to select randomly within those categories. I think when you express multi-stage cluster sampling in that way, when you think about it in that way, it clearly violates random sampling. It is clearly quite different from reaching into the hopper of 50 numbers or however many numbers there are now and picking out 6 in a random way. Are there any questions about either random sampling or about stratified sampling? Or rather, either about sampling or probability sampling? None? Given the discussion so far, I would imagine that you would conclude that even though researchers are typically unable to use random sampling techniques, they would at least habitually use probability sampling procedures. And the irony is that they don't, particularly academic researchers. Instead, academic researchers in particular often rely upon non-probability sampling procedures. Non-probability sampling procedures. And I want to give you one example of non-probability sampling. And these procedures violate the requirement of equal probability of selection and do so in a substantial way, so that the estimates associated with those samples cannot or should not be treated as unbiased estimates of population parameters. The example of non-probability sampling that I want to discuss is accidental sampling. Accidental sampling. You have probability sampling procedures, and we've talked about 2 examples of those. And you have non-probability sampling procedures, and I'm going to offer you one example of non-probability sampling, and that is accidental sampling. If you stand in a shopping mall with a clipboard and a profile and accost people as they go by you, you are sampling accidentally. If you have a telephone directory and you contact the 20th person on every 40th page, you are sampling accidentally. If you require students enrolled in a particular class to participate in a research project, you are sampling accidentally. If you offer extra credit for their participation, that is students, you are sampling accidentally. And I'm willing to bet you that the last 3 of those, that is either using students, requiring students in your class to participate in research, or offering extra credit to students, or using a telephone directory and contacting the nth entry on every nth page. Those 3 procedures are widely used by academics and certainly are widely used in communication. You don't often find academics standing in the middle of shopping malls trying to haul people in, but we might as well. Each of those sampling procedures, and I'll talk about them separately, violates the mandate of random sampling, this notion of equal probability of selection, in a clear-cut way. If you stand in the middle of the shopping mall, there are a host of difficulties. First of all, you have no idea what population you're sampling from. Is it a population of people who shop at the mall? Not necessarily. Some people just wander through the mall on their way, at least, for example, Deerbrook Mall, on their way to the AMC movie theatre. Some people wander through the mall to receive some service, to get their nails done, to get a haircut. So it's not a population of people who shop at Deerbrook Mall. You have no idea what population you're sampling from. Second, some people that you step up to will agree to participate in the research. They'll go off to that little room with you and participate in the survey. And some will not. And the question then is, are the people who agree the same as or different from people who disagree? And it's likely that they're critically different. On the one hand, you have a group who will conform, and on the other hand, you have a group who will not conform. You have people who comply, and you have those who will not comply or do not comply. And it's likely that those two groups differ from one another in a variety of critical ways. Third, those people who stand in the middle of the shopping mall are paid by the number of successes they have, the number of people they cart back to the room. You know, there's evidence that muggers, compared to you and I'm presuming none of you is a mugger, there is evidence that muggers have a more sophisticated schematic representation up here of muggies than do you and I. That is, compared to you and I, muggers can look at groups of people, look at individuals, and in a more accurate way make assessments about how easy or difficult it might be to mug that person. There's evidence of that. I mean, clearly this is the basis for advice that you and I are offered to act in particular ways at night when we're walking through a deserted area or a low population area or through a parking lot and so on. We're advised to behave in ways that suggest we would be difficult to mug. I mean, I'll give you an example. My daughter, who lives in Austin, will occasionally take pity on her poor father and come down and visit him. Make an excursion down here. Actually, it's not so much an excursion as a sort of caravan across the Sahara, one would think. But occasionally my daughter will come down to see me and her mother. I like to think she comes down to see me. She drives back at night, and I have told her, I've tried to get her with only intermittent success to push her hair up and put a baseball cap on, because that way she looks more mild than she would otherwise, and so reduces the likelihood of bad things happening. Because that's just the way the data are. That's just the way the data are. You know, if you open a newspaper, listen to the news, you hear much more frequently of young females being abducted than you do of young males being abducted. You hear more frequently of young females being sexually assaulted than young males. So it's just the nature of the world. You're trying to dress one thing up as another to reduce the likelihood of some sorts of outcomes occurring. You're trying to give the stimulus the attributes of another group. So it's the same with those people who stand in malls with clipboards. You're being paid by the number of people you drag back to the little room. You do this job, I don't know why, but you do it forever. Well, after some time, you're standing there with your clipboard and you've been going up to people and being told, no, I'm in a rush. I've got somewhere to go. And other people are saying, sure, I'll come along, yeah. You begin to develop a cognitive set up here, a schematic representation, cognitive schema, of that helps you distinguish between those people who may well comply and those people who are unlikely to comply. And what do you do when you see somebody coming along who is unlikely to comply? You let them pass by. You let them pass by. And you look quickly for somebody fitting your profile of compliance. So there are all sorts of reasons why collecting data by standing with your clipboard in the mall is simply a long, long way from random sampling. What about contacting every 20th person on every 40th page of the telephone directory? That's a favorite strategy of people in some disciplines. Yeah. I'll tell you, here's why it violates random sampling. Because I can tell you beforehand that your sample will include more people whose last name begins with the letter S than people whose last name begins with the letter Z. Because that's just the way of the world. And if I can make statements of that sort before you've selected even a single individual into the sample, it suggests, to me at least, that you are not sampling randomly. You're sampling arbitrarily. There's nothing magical and there's nothing random about every 20th person on every 40th page, or every 18th person on every 42nd page. That's simply arbitrary. As is using students in classes. And I've conducted research of this kind. Have no idea what population you folks represent. And clearly, that if we imagine that you represent or belong to a population of persons between the age of 18 and 50, we haven't guaranteed equal probability of selection in even the faintest way. Because all those people between 18 and 50 who are right now on their second or on their seventh Budweiser of the day, down in an ice house on Telephone Road, have no probability of selection. And even if they did, I suspect they would decline. Probably in a very gentlemanly, a very personable way. So there is no guarantee of equal probability of selection. What is more, there are some other issues associated with using college students that become critical. In some ways, you are like those peers of yours in the ice house down on Telephone Road. You have some of the same concerns and you engage in some of the same behaviours. All of you date, for example. All of you seek to date. I'm ignoring the people who are shaking their heads like, no, I never date. I don't want to, really. I just want to live by myself and be left alone. There are some areas, however, in which you and your peers in the ice house on Telephone Road are critically different. And some of those ways have to do with cognitive ability. If you're studying reading ability, or reading is involved in the research, for example, then I see no reason to put you and the folks in the Telephone Road Ice House into the same population. And most research involves reading, even if it does not measure reading ability. You're given instructions about what you can and cannot do in the research, what the research is about, and so forth. So, whether you stand in the mall, whether you select names out of a telephone directory, or whether you use students from classes in colleges, college students from your classes, each of those strategies violates, in a very clear way, in a very substantial way, the notion of equal probability of selection. And that being the case, the estimates, for example, the sample mean, the estimates of those samples are biased. They're biased estimates of the population parameter, and so you're back to the position that you were in using unreliable data or from unreliable measures of garbage in, garbage out. Are there any questions about non-probability sampling? Yes.
Technically, what is the difference between random and accidental? Is it random, it's taken from kind of like a whole large section like on the graph and it's like a pieces of it, or?
No, the difference between random sampling and accidental sampling is the difference between Godiva chocolate and that funky 5 and dime chocolate that your grandmother gives you at Easter, you know. Random sampling occurs if and only if there is an equal probability of selection. Random doesn't mean, in this context, accidental. It doesn't mean haphazard. It means that all subsets of size n, that is, all subsets of size n in some population, have an equal probability of selection. When you sample accidentally, that is clearly not the case. That is clearly not the case. If you have somebody with pink or blue hair standing in the middle of a shopping mall with a clipboard, ignoring some number of people, even if they fit a given profile, because he or she believes that they are likely to refuse the interview, then you're not sampling randomly. What is more, to sample randomly, you have to know the population from which you're sampling. And I've tried to illustrate that when you stand in the middle of a shopping mall and try and reel people in as they go by, when you phone every nth entry on every nth page from the telephone directory, or when you use students who happen to present themselves conveniently to you, you have no idea what population you're sampling from. So that there is absolutely no assurance of equal probability of selection. And you have no way of assessing the extent to which your sample has been selected by that mandate. That you had no way of assessing the extent to which your sample was selected, or the way in which your sample was selected differs from random sampling. Are there any other questions? There are none. Let me finish this discussion of sampling then by talking about sample size. Sample size. Let me offer you two examples. Example A, research on a topic in which the sample size is 1,000. The second example is research on a topic in which the sample size is 5. Which research do you place more trust in? A, the research that used the 1,000 persons as opposed to the research that used 5 people. That is, somewhere up here, intuitively, you have greater trust in research that uses large samples as opposed to research that uses small samples. This is like Mission Impossible. Your mission, should you decide to accept it, is to go to WebCT and go to assignment 4. Go to assignment 4. You will find there 10 scores. You will find there an array of 10 scores. What I want you to do is, first of all, select out 5 sets of 8 scores. So you have a group of 8 scores, a second group of 8 scores, a third group of 8 scores, a fourth group of 8 scores, and a fifth group of 8 scores. And in each case, I want you to compute the average, the mean of those 8 scores. So you have X bar 1, X bar 2, X bar 3, X bar 4, and X bar 5. Then I want you to select out 5 sets of 2 scores. So you have 2 scores, 2 scores, 2 scores, 2 scores, and 2 scores. And these needn't always be different scores every time. That is, you don't have to divide these 10 scores into 5 groups of 2. Some scores can occur multiple times. What we're doing here is we're playing as if you're sampling randomly from this population of 10 scores. Half the time you select randomly 8 scores, and half the time you select randomly 2 scores. And in each case over here, I want you to compute the mean of the 2 scores. So again, you have 5 means. And then I want you to compute the mean of all 10 scores. That is, I want you to compute the population mean. And this will take you 15 minutes at the most, this exercise. I want you to then look at 2 issues. One is the consistency of these means versus the consistency of these means. Is one set of means more consistent than the other? Is there less variability in one set of means than in the other? The second issue that I want you to explore is the relationship between each set of means and the population mean. Is one set of means, in general, more accurate than the other set of means? This whole exercise should take you no more than 15 minutes. but it's a critical exercise. It's a critical exercise not only because of the issue of sample size. It's a critical exercise because it should lead you to a better understanding of an issue that is absolutely at the center of empirical research, and that is central limit theorem. Central limit theorem appears in your text as 2 or 3 lines of bold type. If it appeared as in relation to its significance, it would be in 48-point type, and it would be repeated about 50 times across, I don't know, 80 pages. Let me, I'm going to go through this song and dance because central limit theorem is just 2 lines, but if you don't get central limit theorem, the rest of this semester starts to look like a fog. We have talked today, and we've talked previously, and there's no need to write this down. We've talked today, and we've talked previously, about, first of all, a researcher's interest in populations, but second, the need to use samples because those populations are routinely inaccessible. How can you possibly do that? What logic is there? And I don't care how you select your sample. What logic is there in reaching into a population, picking out some number of people from that population, observing those 100 people, or measuring them, or doing something, and then making statements about the entire population? This is absurd. On its face, this is absurd. How can you possibly interview 125 voters and talk about a population of voters? Even if I were to examine all but one person in this class, perhaps interested in GPA, does that guarantee that the one person I have not talked to will fit the profile generated by the others? Absolutely not. Absolutely not. What on earth allows researchers to make inferences about populations based upon the observation of samples? I don't know. Actually, I do know. It's central limit theorem. See, the fact that central limit theorem works is evidenced by your surprise when researchers are wrong. 1% of votes are counted, and researchers are predicting who won that election. And you and I are amazed when those predictions are inaccurate. What is more, researchers don't even have to wait for somebody to vote. They interview 283 people the day before the election, and they make a prediction based on those 283 responses. And you and I are stunned when they're wrong. You and I hear one piece of research reported on the news that links the consumption of red meat to a whole range of negative health outcomes. And we're then reticent to believe anything to the contrary. We suck that information down as if Moses had gone up the mountain and brought a third tablet down and said, "It's here, boys. I learned all about red meat. You know, I got the scoop on red meat. I do not know what you learn in all of those other classes you go to. I don't know what you learn in production classes. I don't know what you learn in articulation classes. I don't know what you learn in public relations classes. I don't know what you learn in journalism classes. But I will guarantee you that whatever you learn doesn't have the magic of central limit theorem. Central limit theorem is pure magic. It is absolute magic, because it is what allows you and I and a host of other people to examine a small subset of a population and then, with a high degree of certainty, make inferences about the population as a whole. And I will guarantee that whatever other classes you're in, you ain't doing that. You're learning where to place the commas and the semicolons. You're learning about various public relations problems. You're learning which button to press when. But you are not learning anything as absolutely magical as central limit theorem. And I do make this song and dance. A, because it's true. And B, so that you don't read through those 2 or 3 lines as if they're of equal value to any other 2 or 3 lines in the text. Central limit theorem is absolutely fundamental to empirical research. This assignment to compute the means and so forth is immediately relevant to the issue of sample size. But as you will see, I hope, next time, it is directly relevant to the issues raised by central limit theorem. Are there any questions? If there are no questions, arrivederci Roma. I'll see you all next time.